In this video, we'll look at question 29 from Unit 4, where we find the equation of the tangent lines to the graph of y equals sine of x. That just begs for a sketch. Here we have sine of x. Here's pi over 2. And what we're going to do is draw the tangent line at the point x equals 0. And we'll draw the tangent line just a little bit back at pi over 3. And compare those two. Draw a tangent line back here. And what we're going to do is compare those to the actual value at some intermediate point, in fact halfway between here, at pi over 6, just to get some sense of how these tangent line constructions work and how to use them in evaluating or approximating a function. So for example here, if we take our x equals 0 as our base point, we have our function, which is sine of x. We have our derivative of that, which is cos of x. And so the tangent line at x equals 0 is, let's call it L1 of x for linear 1 or line 1. It will be the derivative, cos, at 0 times x minus 0 plus sine of 0. And all that is our f prime at the point we're looking at, x minus the point we're looking at, plus the y value or the function value at that same point. A here in all these locations is the point we're using as our reference. Here it's x equals 0 or a equals 0. When we simplify that, cos of 0 is 1, x minus 0 is just x, and so we end up with that very simple function, y equals x. So this is L1 of x, and it's just a straight line with 0 intercept and slope 1, and it's just equal to x. That's not the only tangent line we can build though, we can build multiple ones. Here we're asked to build a second tangent line at pi over 3. Again, that's this black line. We go over to pi over 3, draw a tangent line there, and that'll be our second line, call it L2 of x. The construction is exactly the same, except everywhere we had a 0 before, we have a pi over 3, because that's the point that we're using as our base or reference point. You can use your calculator at this point, or you can draw one of our classic special triangles, where we have 1, 2, and root 3. Pi over 3 is this angle down here, 60 degrees. The cos of that is adjacent over hypotenuse, is 1/2. And x minus pi over 3, plus the sine, which is the opposite over hypotenuse, which is root 3 over 2. And that defines this curve here, L2 of x. We won't add it to the graph at the risk of complicating the already complicated diagram there. But this gives us a function that we can follow this black line around on and ask what's the value of that linear approximation or that tangent line at any point. And our next stage is to evaluate it specifically at pi over 6, halfway between those two locations. So with those two expressions, when we plug in x equals pi over 6, here we're going to get L1 at pi over 6 is just, wait, pi over 6. That's not too interesting. It's helpful, or more helpful, to compare it to something else. When we do the second linear function and evaluate it at pi over 6, we end up with pi over 6 minus pi over 3 plus 3 over 2 gives us approximately 0.6042. And for reference, this pi over 6 value is going to be around 0.5. It's approximately 0.5236. Now, let's compare that to the exact value, or at least to a few decimal places. The exact value of sine pi over 6. Make sure your calculator mode is in radians, or go back to your special triangle, and you actually get that equal to 1/2. And so what we have here again is, from a diagram perspective, we have the sine graph, we had the tangent line initially here, we had the second tangent line back here. Both of those end up a little high. Here's the actual value of our function. Actually, it's probably closer to here. And one of these lines is a little bit closer than the other. The y value of this is 0.5. The y value of the blue line there is 0.52. And meanwhile, the black line's value at that point is a little higher. It's at 0.6042. That leads us to our next question, which is, would you expect these results to be equally accurate, given that, as we said, we're going to take them at equal distances away from pi over 6. We're going to go one step over here to 0, or go the same distance the other direction and draw tangent lines. And what we want to know is, should we have expected exactly the same accuracy? And we can see clearly that from our values, one of these is more accurate. The green one, which came from the first estimate, is more accurate, at least over this distance. And the question is, well, why might that be the case? Well, again, if you think of how tangent lines work, we're following a straight line. And if you think of how the sine graph looks, it starts off pretty flat and then bends more aggressively. It has something to do with the curvature. The less bend there is in the function, the more accurate a straight line approximation is going to be. And if we compare 2 points, one which is in the middle of this big bending part of the graph versus one that's drawn where the graph is straighter and has less bend, we expect here to get the linear approximation, or the tangent line, to be more accurate on the same distance anyway, because the function underneath this sine of x here is less curved. For those who like their second derivatives, this would be something about the second derivative and how large in magnitude that second derivative is here, or at least on this interval, versus on this interval over here.